Hi, welcome back to A Slice of Physics. We're now going to talk about Ohm's Law, resistance, and resistivity. Ohm's Law helps us determine how the magnitude of current depends on the potential difference across the wire. We already know that the direction of current is such that positive charges flow from higher potential to lower potential, but we want to know how much current a wire carries. And in doing so, we will meet another quantity called resistance. So we will understand what resistance in a circuit is. We'll take a look at what factors affect the resistance of a wire. And one of those factors is something called resistivity, which is a property of the material from which the wire is made. And since we have two words that sound very similar and you tend to sometimes get them mixed up, we will clearly define what is what, so we have the right foundations for going forward and working with these quantities. Continuing our water analogy, let's take a pipe that is laid out like this, where you've got a higher potential at the top and a lower potential at the bottom. And we saw in the previous video that this causes a current of water, in this case, water to flow in the pipe in that direction from high potential to low potential. And the same thing is true in an electric circuit. So I've got a wire over here, and let's say I've got high electric potential over here and lower electric potential over here, and I don't need a height difference to have different electric potentials, so I'm just showing it as a flat wire. Then we know that the current will go from high electric potential to low electric potential, so this way. So we know the direction of current. The question is, what would be the magnitude of this current? How much current is going to be in this wire? Relating back to water, if I created a different pipe with a larger potential difference between the top and the bottom, that this might increase the flow rate of the water through this pipe. Same thing is true in the electrical sense. So if I have the potential difference between the two ends, let's call that delta V, the higher the delta V is, the higher the current would be. The second thing that controls the flow of water is the resistance to the flow. So for example, let's say I go in here and throw some boulders into this pipe like that. Now you would expect the water flow to decrease when that happens. So it'll no longer be the current it was, it'll be a smaller value through this pipe. So that's the topic we're talking about. So in the electric circuit also, we have a notion of this quantity called resistance, and resistance simply opposes the flow of charges, and flow of charges is current, so resistance opposes current. So the higher the resistance, the lower the current would be. This relationship is given to us in a mathematical form in Ohm's law. Ohm's law states that the current in a wire equals the potential difference across the wire divided by the resistance in the wire. So let's take a look at this equation. As you can see, as delta V increases, I would increase, which we mentioned here, and as R increases, I would decrease, which we mentioned here. So the relationships are appropriately captured in this equation. Let's also take a quick look at the units. We know the unit of current is amp or amperes. We know the unit of potential difference is the same as the unit of potential, which is volt. And so what would be the unit of resistance? Well, we can rearrange this equation to say that resistance equals potential difference over current, which would then be volt divided by amps, and that's given a different name called ohms. And it's written with the Greek letter omega, capital Omega. One other quick point about current here. We see that current has magnitude, and that's the rate of flow of charge, how much charge goes through a point in the circuit in 1 second, and it does have direction. So this magnitude is delta Q over delta T, or as we just learned, it's also equal to the potential difference divided by the resistance. And the direction is from high to low potential, more specifically high to low electric potential. Now, even though current has magnitude and direction, it is not a vector. And that's because if I have a wire that's laid out like this, and let's say I have a current of 2 amps coming in here and I got 3 amps coming in here, they will come to this junction and they will leave the junction with a total current of 5 amps. We will see later why this is, but the current in a junction is conserved. Now, if these were vectors, 3 amps pointing to the right and 2 amps pointing to the left would only give me 1 amp pointing to the right. So neither the direction nor the magnitude of this resultant current would be correct. And by the way, even if I change the configuration of this junction to be something like this, and have those currents of 3 amps, 2 amps coming in, it'll still be 5 amps going here. So it really doesn't depend on the geometry of it. And since we can't work with it as vectors, it is not a vector. So let's clear all that work and summarize Ohm's law here as I equals delta V over R. And by the way, we can rearrange this to write delta V equals I times R, and we will use this form frequently when we work with circuits. Now, one thing to note, this Ohm's law is not a universal law in the sense that it doesn't apply in all situations. It only applies when the materials involved are called ohmic materials, and those are materials where the resistance does not change with the current. So the resistance does not depend on how much current it carries. That's true in many situations that we will work with. In fact, in almost all the situations we will work with in this course. But when you look at what happens inside a battery, the current inside a battery is not a function of its resistance. It's rather a function of its capacity to conduct chemical reactions to move charges from one end to the other. And capacitors also do not work as ohmic materials. But wires, bulbs, other kinds of resistances we will work with in this course are all ohmic, and they will follow this law. So to understand a little bit more about resistance, let's see where it comes from. So if I have a wire which has a potential difference across it, so there's one wire and here's another wire. It's just a lot thicker and it's got the same potential difference across it. Which one of these do you think would carry more current? Well, your intuitive feel would lead you to the right answer. So this would carry a smaller current and this would carry a bigger current. Just like if this were water pipes, this pipe would carry more water for the same potential difference. So the thicker the wire is, the lower the resistance is. Remember, the current and resistance have an inverse relationship. Second, if I have a wire that is a short wire with a given potential difference and another wire that's much longer and has the same potential difference across its ends, you might think that the shorter wire would carry more current, and that again would be correct. There'd be more current here because there's a lot more potential difference per unit length as compared to here. So in the gravitational analogy, this is more like a steeper waterfall than this is. It falls more in a shorter distance. And the third condition is what the material itself is made of. So if I have a wire that's made of copper, for example, or I have another wire that's made of iron, let's say, those would have different resistances. So let's summarize these dependencies. So here I'm looking at the cross-sectional area, let's call that A, and we see that current is bigger in a wire with a bigger cross-section, which means the resistance is smaller. So as area increases, resistance decreases. Then we looked at the factor of the length of the wire, and here we saw that the longer the wire is, the less the current, which means the bigger the resistance. So longer the length, bigger the resistance. And then thirdly, we saw that it depends on the material. And in this case, this was copper and this was iron, and we know that copper is a better conductor, which means it's got lower resistance. And we call that factor of the material of the wire something called resistivity, which is written as Greek letter rho. So this is resistivity, and it strictly depends on the material of the wire. So you can think of this as the boulders in the pipe that we talked about earlier in this video. So iron has more boulders and hence a higher resistance. Copper has fewer boulders and offers a lesser resistance to current. And so the unit of this resistivity is ohm times meter. And we'll see how that works out when we discuss the actual mathematical relationship of resistance, as it depends on these factors. And just to give you some examples, when I have copper, its resistivity is something like 10 to the negative 8 ohm meters, whereas iron has a resistivity of something like 10 to the negative 7 ohm meter. So iron's resistivity is about 10 times that of copper, and that's what makes copper a better conductor of electricity. So clearing some room here, let's talk about the relationship between all of these things. The resistance of a wire is given by this equation, rho times L divided by A. So the resistance in a wire equals the resistivity of the material with which the wire is made times the length of the wire divided by the cross-sectional area of the wire. And from a unit standpoint, the unit of resistivity is ohm times meter, the unit of length is meter, and I got to divide by the unit of area, which is meters squared, and you can see that all of these meters cancel, leaving me with the unit of ohm, which is the correct unit for resistance. Okay, so this is how resistance of a wire depends on its physical properties, and here's how the current in the wire depends on the resistance of the wire and the potential difference across its ends. So to summarize, in this slice of physics, we first saw how current is dependent on the potential difference across a wire and the resistance of the wire, and that relationship is mathematically given by Ohm's law, which is this equation, I equals delta V over R. And this works for, as we discussed, ohmic materials, where the resistance does not depend on the current in the wire. So the resistance of the wire in these situations depends on the physical properties of the wire or the resistor itself. So there were three factors in this. The first one was the resistivity of the material with which the wire is made. The second factor was the length of the wire, and the third factor was the cross-sectional area of the wire, and the relationship between those three properties was captured by this second equation. Thanks, and in the next video we'll take an example to work through these equations.